So let's continue looking at another linear mathematical model where we're focusing here on first order linear differential equations. And one application is Newton's law of cooling or warming. Okay. If a body has a temperature of T with a lowercase t time, okay, at time t, and is in thermal contact with another body with a constant ambient temperature Tm. So in general, if you take one body of a certain temperature and it's in thermal contact with another body, both bodies will change temperature. Okay, one will cool and the other will heat. But we're going to assume that the other body, the one that we're not interested in, the ambient one, has a constant temperature. Okay, and what does that mean? It's just a large thermal reservoir. Okay, that's what we mean by assuming that it's constant. So we're going to assume that it's a large thermal reservoir. Okay, if you have a hot needle, for example, and it cools down while sitting outside, it barely changed the temperature of the atmosphere around it. Okay, so that's a pretty good approximation that the outside temperature is constant. Okay, so how do we solve this? We could solve this using separation of variables again. And we just crank through the algebra after integrating. We have this absolute value, okay? So you got to be careful around these absolute values when you integrate. And we do end up with a constant of integration that I fix using the initial temperature. Okay, and you could get problems where, you might not want to fix that parameter to the initial temperature. But here I just do it for simplicity, okay? If you're given a problem where you're not given the initial temperature, but say the temperature at some particular time, other than the initial time, then you could fix you might just want to integrate yourself and fix this constant according to the time given. Nevertheless, if we let t naught equal t at t equals 0, then when t naught is greater than or equal to tm, this here is positive, okay? And so you could just ignore the absolute value sign there. That's what the absolute value means. If it's positive, it does nothing to it. And you can fix then c to t naught minus tm. On the other hand, if t naught is strictly less than tm, so that this is negative, then so the absolute value would multiply the negative term by -1 to make it positive, okay? So that's its operation. It takes negative numbers and multiplies them by -1 to get positive. It takes positive numbers and does nothing to them. And c would be this right here. And so we could write that out, okay? But notice you'll get a double negative. So c here would be negative in the case that t naught is less than tm, okay? Which when solving this equation here, okay, we'll have another minus sign, and these two minus signs cancel. So you actually end up with just one form that you have to worry about there, okay? And so this is the general form of the solution for Newton's law of cooling or warming when you set when one of the parameters that you have is the initial temperature or the temperature at t equals 0. Okay, so let's look at an example of Newton's law of cooling. When a cake is removed from an oven, its temperature is measured at 300 degrees Fahrenheit. 3 minutes later, its temperature is 200 degrees Fahrenheit. How long will it take for the cake to cool off to a room temperature of 70 degrees Fahrenheit? We're not given K, the constant of proportionality, okay, between the difference of temperature and the rate of change. Okay, that's going to depend on the material involved and all sorts of things. We just simplify by saying it's just K. Okay, there's only one parameter. We're going to take in all these different factors and just have this cooling or heating constant. And we'll solve the differential equation again here, just to go through it. So Tm is 70 degrees Fahrenheit. And that's why we have a 70 there. T0 is equal to 300, the initial temperature. And we're basically going to solve for K because we don't have it. But we have two different data points, okay? The temperature at T equals 0 and the temperature at T equals 3 minutes. And from that, so, solving this differential equation, we get this, which follows the same form up here, by the way, as we should expect. And you end up with this relation, okay? And now what are you going to do to fix K? You're going to have the two different pieces of information. The left-hand side is the condition given in the problem, okay? And the right-hand side is what we would get when we plug in 3 minutes into our general form. And we could then solve for K algebraically. We end up getting, after taking the natural log and simplifying, we end up getting this rate of temperature change, okay? So this is the amount per minute. It has a unit of per minute there because of the 3 minutes we plugged in. And now we have our general temperature form. Now, if you try to plug in 70 into here, okay? So if we do this generally, we would say 70 is equal to T at, let's just call it T sub 70, the special time. Instead of writing this again, I'll just put K of T just to make a point here. And notice that these 70s would end up canceling, and you actually end up getting 0 is equal to EKT. Now, is the exponential ever 0? No. So no solution. Okay? This never ends up reaching a temperature of 70. Okay? But we do have that it asymptotically approaches it. Okay? This goes back to the autonomous differential equations. This is an autonomous differential equation. And so you never quite approach the equilibrium solution of temperature equals 70. Okay, so if we start with a temperature of 70, it just stays there. This is an equilibrium solution. It's an attractor. You could see that from the phase portrait that I draw here. You can see that the phase lines move towards the Tm. It's an attractor and it's stable. This here is a transient term, okay, which you could see here. Why? Because as t goes to infinity, this goes to 0. Never hits 0, but goes towards there. And for our purposes, you could say that after about t equals, say 4K, it's as good as close to 70 as we would care, okay? And so you could say, well, technically it never hits 70, but after about t equals 3 times K or 4 times K, then it's good enough close to 70 for our purposes, depending on what you're applying this for, okay? Obviously, you wouldn't need the temperature to be like at the 10th decimal place close to 70 if you're just cooking, right? Or something like that.